All right, this is the third lecture. Let's see where we are in our journey. Last week, we talked about how ML works. This week, we will stay on the same topic, but we'll be a little more specific. In particular, there are two broad applications or use cases for making predictions, and those are regression and classification. And we'll talk about those two. Let's review what we talked about so far. I presented to you a recipe for machine learning. I told you that there are these two steps or two phases in a machine learning project. You have a training phase and you have inference. And training is when you get all the examples of known inputs and outputs, feed it into this algorithm to learn from. And once it has learned those underlying patterns, you can use it. You can give it input of an example for which you want to know what the output is. And then the machine learning algorithm will predict the correct output. And then we looked more closely into that robot, and I said the training piece is essentially a learning algorithm that ingests these data and comes up with a model. And the model is a mathematical expression that maps the input to the output. And we looked a little more closely at that model. Like I mentioned, it's really a function or a mathematical expression. And I introduced some new notations, x being input, y being output, the superscripts being the sample number, and the hat here representing the predictions. And finally, I brought in the example of a housing price, and I presented to you what the most simple form of that mathematical expression or the model would be like, which is a function of a line or a linear regression equation represented as W0, which is the intercept of the line, plus W1x. And this is what that line looks like. And the whole purpose of training is to tweak the values of W0 and W1 to make the best predictions. And that's already quite a long way from where we started, where we said machine learning is about learning from examples, to saying that the learning process is really about tweaking the model parameters to make the best predictions. And we went a little bit farther, and I showed you the training in action, which is an iterative process. And during that iterations, the values of model parameters get more tweaked, and the prediction get more accurate. And each of those iterations is something like this. You already have a model, you feed it the data, the inputs of your training examples, it makes some predictions. You take the x's, the predictions, and the actual labels into this gradient descent to determine in which direction you have to tweak the model parameters. Should you increase W's or should you decrease them? And with that, you will come with a updated set of model parameters, and you repeat this loop. And finally, I gave you this visual representation of what that could look like. You start with some random model parameters, and as you iterate, you find the gradients with respect, the gradients of loss with respect to each model parameter. You update the model parameters, you iterate in that loop, and the model gets more and more accurate. And I presented this simple API for training defining a model, training it, and making predictions with it. Here the idea is that even though under the hood there is a lot of things happening, for you as a practitioner, you don't need to write a lot of code to make it happen. So that's everything we talked about last week. And with what I presented to you so far, you can come up with models, with machine learning applications, for everything you see on the left side of the screen. You can use it to predict house prices, which is what we did, weather forecast, the temperature tomorrow at this time, the stock prices, the drive time, how long does it take to go from this point to another point, the gas prices. And if you think about it, the model doesn't even know what a house is, right? It just had a bunch of inputs and an output and try to come up with model parameters that make the best predictions. So you could use it for any of these. But you can't use it for anything on the right side of the screen. Here, like you have spam detection, where the input is the content of the email and you want to predict if it's spam or not. What we talked about can't be used for that. Or for image recognition, whether a transaction is fraudulent or not, whether the Facebook users will click on an ad or not, and whether the bank should approve a loan or not. I want you to take a moment, maybe pause the video, think about how these two groups of applications are fundamentally different, such that we could use what we have learned on one set, but not on the other set. Well, fundamentally, the two are different in that on the left, you're trying to predict continuous values like price, like temperature, height, weight, so on and so forth. The ones on the right side are categorical. They are discrete values. It's either spam or not. The image is either of a cat or a dog or a horse or something, so on and so forth, right? So these are the two broad categories of the target variable that you're trying to predict. And accordingly, there are these two family of machine learning applications that we call regression for continuous variables and classification for categorical variables. So far, we talked about regression only because we focused on house prices. But let's shift our focus today to classification. The example that I want to walk you through is that of predicting whether a tumor is cancerous or it's benign, not cancerous. And that is based on the size or the diameter of the tumor. So if I plot the tumors and their true nature on this horizontal axis, where the diameter increases from left to the right, and the color represents whether the tumor is benign, blue, or cancer, orange. This is what the data looks like. And the purpose of classification would be to take the tumor size as input and be able to predict if it's a cancer or non-cancer type of tumor. And essentially, the model you're building here would come up with this point, this tumor size, this threshold. And then it would say anything smaller than this, I'm going to predict to be not cancer, and anything larger than this, I'm going to predict it to be cancer. Well, even as you can see in this example, the lines are not always doing a 100% perfect job in splitting the data into cancer and non-cancer, but that's just the nature of making predictions. That's not going to be 100% accurate at all times, but it's going to be pretty good, much better than random guess. Right. And this idea of having this line that separates the space into two classes, cancer or non-cancer, this is what we call a decision boundary. And very often, the task of training a classification model is to find that decision boundary. Now, let's look at this tumor example a little more closely. Similar to housing price, where you can't realistically predict the house price based on the area only, and you need other features. The same is true about predicting the true nature of a tumor. Say we have an additional feature, which is the patient's age. Here, I would have the tumor size on the horizontal axis and the vertical and the age on the vertical axis. And I'm putting my non-cancers as blue and cancer as orange, right? So this data point, for example, the one I'm pointing at, represents a tumor that was for this age and this tumor size, and it was not cancer. In an example like this, your classification algorithm tries to come up with this decision boundary, maybe like this. Again, to separate the space into cancer and non-cancer, such that any point that lands on this side would be predicted as a cancer, and any point lands on the opposite side would be non-cancer prediction. So a dot like this would be definitely predicted as a cancerous, right? So this is what a classification model tries to do. Now, with the intuition you have about classification and regression, let's look at a few examples and try to see if we can figure out if these problems are classification or regression. The first one, the school builds an ML application to predict which students need counseling support. Here the use case is, so you have the counseling center or mental health support center in the university. Well, it would be great if the students with need for help will come in and seek support. But very often, those who are actually in the most severe need won't show up. So it would be nice if the school could be a little proactive and reach out to the students. Now, you want to build an ML to look at the various features of the students in the campus and figure out who are the ones that the school needs to reach out to. Is it a classification or regression? All right. I believe that would be a classification, because for each student, you're trying to predict, is it of class 0 or class 1? Is it of no need or of need? Second example, Honda builds an ML application to predict the mileage of a new car design concept. The idea is they don't want to spend hundreds of $1 million building a car, manufacturing it, just to find out what the mileage is. It would be much better to be able to predict what the mileage is going to turn out. And an added benefit of this is that now you can quickly iterate over your car design to reach the best mileage before you even build anything. Would that be a regression or a classification model? This is a regression model because you're trying to predict mileage, which is a continuous value. And finally, this is a tricky one. You want to build an ML solution to make money on the stock market. I kind of left it vague because there are many ways you could go with this. And so here how I imagine this could work. You could go either way. You can build a classifier or a regression model. The regression would be as follows. You build a model that predicts the price of a particular stock for tomorrow. And a classification model would be one that predicts whether a stock is a buy or a no buy tomorrow. Personally, I think the regression model will make a lot more sense than classification, because with classification, it's going to be a buy if the price tomorrow is going to be higher than today, even by 1 penny, which may not be worth it. Whereas with regression, you have a lot more granularity or insight into how much gain is there to be made. Right. Anyways, the whole idea is that this regression versus classification is not always a divine thing that will come to you. Sometimes you get to choose how you want to tackle this problem and design your ML solution. Now, let's go back to our tumor size. And I want to talk about how you can build a model. I explained what the classification is, what it tries to do, but let's talk about how it works. And the good news is it's actually very, very similar to what we have already built. And let's start, as a matter of fact, by talking about why can't we just use what we have already built with regression for classification use cases. Let's look at this. I have tumor size, and the dots are colored differently to show the classes. But I could make it a little more useful by just showing one color, but plotting this vertical axis that shows whether the class is 0 or 1, right? So the dots at 0, y equals 0, mean their label is 0 or are not cancer. 1 means cancer. And in classification, generally, you label classes as 0 and 1s. So we can plot it in this way, and this is essentially the same as what I described earlier, just different visualization. And when you look at it in this light, you may say, you know what, I could fit a linear regression model to this, just like this. And I would say, I'm going to find where the 0.5 is, which is right here. So this is 0.5, right? And that becomes my decision boundary, like this. Anything where the y hat, the prediction, is less than 0.5, I'm going to predict it to be benign. And if y hat is larger than 0.5 on this side, I will just predict it to be cancer. And that could work. However, I'm going to show you how this may not be ideal. Imagine you have an additional point that's to the far right. Logically, this should not make any difference in our predictions, in our model, because this is way in the zone where we predict the class to be 1. So our model should be robust to this. There should be no changes to our model in light of the presence of a point like this. But that turns out to be not true, because if I fit a line now in the presence of this new data point, the line is going to become much inclined towards this new data point to minimize the error, right? And suddenly, where the threshold was up here, you can still see this orange line that I plotted before. Now it's been moved to here. And a lot of data points that were cancer are going to be predicted as non-cancer because they're on the left side of this new threshold, right? So there are really two reasons why you don't want to stick around with this linear equation for making predictions. One is that it's very sensitive to these outlier data points that are going to move the line, move the threshold where you know they should not. That's one. And the second is that the values of the predictions could be anywhere from minus infinity to infinity. Whereas you know the true outputs should be between 0 and 1. Your labels are never greater than 1 or never less than 0. And in fact, it would be much better to have a model that make a prediction between 0 and 1. Our approach is going to be, you take this line, this linear equation that we have, and pass it through a function or a transformation that squashes the values between 0 and 1, right? And that's what I'm talking about. All right, so what do we do? The approach that we typically take in classifications is we stick around with this line that we fit on the data, but we don't use it directly. We feed the predictions of the line into a function or a transformation that squashes the values between 0 and 1. So what I mean by that is that if you take this orange line and pass it through that function, you get something like this new line. And what is beautiful about this is that the outputs are always between 0 and 1, and we will interpret that as the probability of the output being 1. So if the final output that comes out of this transformation is close to 0, you're going to say, well, the model predicts a very low probability that the label is 1. And if the values are close to 1, you will say that the model predicts with high probability that the label is 1. And this transformation, this function that takes any input and squashes it between 0 and 1 is called the logistic function. And this algorithm that tries to classify data into 0 and 1 by using a linear function and then feeding it into a logistic function is called logistic regression. Now, if you look at the recipe that I gave you, what you'll notice is that the only thing that's different here for classification versus what we already talked about for regression is that the mathematical expression, that function, the model, is not just W0 plus W1x, but rather you feed it into this other transformation, which I refer to as a logistic function, to squash it between 0 and 1. Right? So your mathematical expression has been changed a little bit compared to a regression problem. And now you take that and you plug it into your inference pipeline. And if you notice, regression and classification are very similar. Everything we learned so far about the loss function, minimizing it, gradient descent, all of that still holds true. The only thing that really changed here was that mathematical expression, the model itself, and we're forcing it to make predictions between 0 and 1 by introducing this logistic function on top of the linear equation. The API, again, looks very similar to what you had for linear regression. And I want you to notice what is different here, and that is instead of importing a linear regression model, you import a logistic regression. But the rest are essentially the same. All right. So in summary, what we learned today is that there are these two broad categories. You have regression and you have classification. And the two are almost identical under the hood in the way that the machine learning works, except that for classification, you want the predictions to be between 0 and 1. And for that, you take your linear function and put it into another transformation that we call logistic function, and hence the name logistic regression. That's it. I hope that was useful.